Now we're going to take a look at section 5.2.3. And we're going to have one very, very clear goal within this section. And it is going to be, how do we determine if we have a normal distribution if a problem doesn't say so? So as I state here, many of the inferential procedures that we'll start to study in some of the chapters to come will either require that we have large samples or will have data that comes from a normal distribution in order to be able to kind of proceed with some of these problems. So understanding if data comes from a normal distribution is going to be very important for us. So with textbook problems, or a lot of things that are often kind of manufactured, we're often just told, assume data are normally distributed, or assume the light bulbs have a normal distribution, assume that the tree heights are normally distributed, right? So we have different things that are like that. But if we're actually collecting real world data, we're not really going to be told whether or not something has a normal distribution already. We're going to have to be able to determine that just from the raw data itself. So when collecting real-world data, we need to be able to check to see whether or not it's a reasonable assumption to believe that the population that we're sampling from is in fact normally distributed. Now on the formula sheet, you'll see that this is represented right down here in this middle column where we say that how would I check to see if a distribution is normal? Well, we either have that the textbook would just say so, or we can use raw data to construct a normal probability plot. And it's this portion down here where 5.2.3 comes into play. It's how we actually tackle this particular check. Nothing else in the column is going to change. This entire section focuses just on this one little phrase. So let's see how this actually works. A normal probability plot is a graphical display. It's a picture. And it's going to help us display quantitative data, and it plots each point essentially against its z-score. Now, ultimately it can get a little bit weird in understanding exactly how all of this works, but here's kind of at least the basic gist. If these values match up fairly well, that is, the data point to its z-score, then what we'll see is that we'll get a bunch of dots in a picture that roughly form themselves into a straight line. And if that happens, we will choose to believe that our distribution is normal. We'll believe it. We'll assume it. We don't know it for sure, but it's a pretty safe bet. If these values do not match up well, then the plot, or the dots that we'll see, will bend. They'll be curvy, or not in a very straight line. And that would give us reason to not believe that the distribution that we sampled from was normal. To get a sense of how we'll go ahead and do this, let's take a look at example 1 and the calculator commands that we have right here. So example 1 says, a sample of graduate students was taken in order to try and determine the average ages of all graduate students at any town university. Can we assume, based on this small sample of graduate students, that all graduate student ages form a normal distribution? So that's kind of a tough question here, right? Notice we only have here, what is it, this like 15 graduate students? And we want to know if we can safely conclude that all graduate students form a normal population? Well, that's the goal here of this section. How do I use this small sample to make an inference about the entire population? All right, so let's switch over to our calculator and see how we can actually go ahead and create one of these normal probability plots. Okay, so the first thing that we're going to have to do is actually click on the Stat button and go to our Edit command, and we want to enter all of our information here into a single list in the calculator. Notice I'm saying I want to insert it into a single list. So although it looks like my data was set up on the page with 3 different columns, I'm going to go ahead and start typing in my values, say from column 1, and then I'm going to immediately continue to type in the values from column 2, and then immediately type in the values from that third column. So in total, I should have 15 total results. Okay, so you should be able to go ahead and do the same thing. Now to have the graph create this picture, I'm actually going to click on the second button now, and then my y equals. I'm going to go back to stat plot, where we would have made things like box plots before. So I'm going to go ahead, click underneath number 1. I'm going to make sure that I turn it on, and then I have to select the appropriate type of picture for the type. I'm not creating a box plot. I'm actually going to go and select this very last option over here, and you can get that by clicking the right arrow. Okay. I'm going to click the right arrow. Finally, I'll click Enter. And once I click Enter, it'll update the rest of what it requires on the page. the first thing it wants to know is, where's my data? Well, I already put my data in list 1, so I don't have to change that. But if you put yours in a different list, you might have to adjust. This value here, the data axis, we're never going to have to change that. Just always leave that as X. Pretend it's not even an option. Everything else here is just something for you to go ahead and try to customize your picture to be unique in your own person. Okay, we don't care about any of that, so let's just go ahead and say, I want to see the picture. To see the picture, remember you can always click Zoom, and then down at option number 9 is a zoom for stats. So if I do that, here's a picture that I end up with. Now, I want to be able to go ahead and confirm that, or be able to demonstrate that I was able to create this picture. And you should want to do the same thing. If this was on some sort of an assessment or like an exam, you would want to draw this picture down. And so to illustrate that, I'm going to go over here to the notes, and I'm actually going to go ahead and draw this picture out. So I'm going to go ahead, I'm going to put out a big screen like this. I'm even going to go ahead and put across the middle here, I kind of have this like horizontal line. Let's see, I'll flip back. Yep, right, I have this horizontal line here, and I'm just going to provide like a rough sketch of what the picture looked like. Okay, so let's see. This doesn't have to be a fantastic work of art. Don't worry if it's not the most beautiful picture you've ever created in your life. I just need to have the general gist of what this picture looks like. All right, so we had something that kind of looked like this. I'm kind of just drawing in a couple of these things, and then I had something that kind of went like that, right? So this is roughly what the picture looked like. Now the question is, are these data points here roughly kind of guiding in some sort of a straight path, or are they in some sort of a bendy path? Well, it's probably pretty easy to see here that they kind of roughly line up in some sort of a linear fashion, right? They're not, again, perfectly able to like connect the dots with and form a straight line, but they seem to kind of not be scattered all around the page or be bending and warping in different directions. They kind of all seem to be moving on this slight upward tilt. So we can say here that the data appears to be linear, appears to be in the shape of a line, and so we could answer the question. We could say, yes, it is reasonable to assume the data of graduate student ages comes from a normal population. Or another way to say that would be that we could say the population of all graduate student ages form a normal distribution. That's it. So again, what we're doing here, and it's very important to see this, is we're trying to take our best guess. We want to see, based off the data that we have, is it a safe bet to say, you know, I think all the graduate ages, if I got all of them, I think we'd have something like a bell-shaped curve starting to form. And we determine that by looking at this picture and seeing if it's in the shape of roughly a straight line. Now, as I state down here, it's reasonable to assume data came from a normal population if the normal probability plot is roughly linear. Keep in mind, though, this does not prove that the population has a normal distribution. It's just telling us whether or not it's a reasonable assumption. It's an educated guess.